Hi, and welcome back. Example 11.8 on uniform circular motion. In this problem right here, there's actually a value that should be added in, or a given that should be given to you. Now, with it as is, you can solve it, but it's really not a solution. It would be a solution in terms of the coefficient of static friction. So we're asking, how fast can you get a turntable spinning before a coin slides off? Well, that really depends on how much friction there is between the coin and the table. And so we could solve it this way, but let's make it easier on ourselves, or at least more solvable on ourselves. But we're going to state that the coefficient of static friction is 0.8. Okay, I just made that up. Let's just pretend it's a fairly sticky turntable, okay, and the coin is sticking on there for a while. Let's solve it in terms of, let's just solve it using this as a given right here. Okay, so we have a radius of 15 centimeters. And we all know to convert that to meters, 0.15 meters. And our coefficient of static friction is 0.8, and there's no units right there. And we want to find the largest speed, or in this case, speed doesn't necessarily mean velocity. In this case, speed is defined as, well, really as frequency, or RPM. Okay, so A is really asking us, what is the frequency in RPM, or revolutions per minute? That's what we want to find out for part A. Okay. Well, remember, and let's draw a free body diagram right here. Here's our turntable. There's a little spindle right in the middle there, and our coin is sitting right there, and our turntable, we'll say, is going around counterclockwise. Okay. Well, the tendency of the coin to fly out, you might call centrifugal force. It really isn't, but it's caused by the centripetal force, because of its acceleration. And the idea is that is balanced out, or the largest speed means that there's a balance between the inward pull of friction. I shouldn't say the inward pull, really the resistance of friction, resisting the outward tendency of the object to fly out, caused by centripetal acceleration. So really what we're saying here is that the static friction force has to be set equal to the centripetal force, or the net centripetal force on that object, on that coin. Okay? Well, we also know that the net centripetal force can be written another way. That's the mass of the object times the centripetal acceleration, which we know all kinds of ways to solve for that. And now you might say, well, we don't know what the mass is. And you're right, we don't. It's just a coin. We don't know how big it is. But we do know also that we know how to find the maximum static friction force. That is the coefficient of static friction times the mass times gravity. Or it's really the coefficient of static friction times, that's the normal force right there. Okay. So let's solve for the centripetal acceleration, which we don't know yet. We don't know this right here. Now, what are we ultimately solving for? We're ultimately solving for the frequency. But we know there's a relationship between centripetal acceleration and frequency. So let's solve for this first, and then solve for frequency. Well, looking at this relationship right here, we can see that these m's are going to go away. These masses cancel out because it's the same mass of the same coin. So if you solve for centripetal acceleration, this mass goes down below and they cancel out. So AC is going to be equal to simply the coefficient of static friction times gravity, or 0.8 times 9.81 meters per second squared. And that is 7.85 meters per second squared. 7.85 meters per second squared. That is our centripetal acceleration of the coin. Okay, or we might say the maximum centripetal acceleration it can have if it's going to not slide off. Okay, so that's the maximum it can have if it's not going to slide off. So what we want to find out is what is a frequency that would cause that centripetal acceleration. Well, again, go back to your equations for centripetal acceleration. We'll find one that looks like this. Centripetal acceleration can be solved by taking 4 pi squared times the radius just by itself times the frequency squared. Well, now we can solve for frequency because we know everything else now. Frequency, I'll do this in 2 steps here. Frequency is going to be centripetal acceleration divided by 4 pi squared r. So therefore, frequency will be the square root of, oops, that was a bad square root. That's all just bad. Let's just do that all again. Centripetal acceleration, we just found that 7.85 meters per second squared divided by 4 pi squared times the radius, which is 0.15 meters. And I actually have to calculate this here because I added this. I actually changed this and I added this at the very last minute, so I don't actually have this done here. So I'm calculating this right when you are. 4 pi squared times 0.15 squared I get 2.9, we'll just say 3.0 over seconds. Okay, or we might say revs or cycles per second. That's our frequency, okay? I think that's what we should get. Did I do my math right? I'm pretty sure I did, yeah. Okay, now, so this is our frequency, or we could say it's 3.0 hertz, okay? But, well, we actually want our answer in RPM, so revolutions per minute. So let's convert that. Let's just use revolutions per second and convert to revolutions per minute. 3 revolutions per second. We can do that pretty easily. 60 seconds to 1 minute times 60. I could have done that in my head. 170. Well, actually, if you take 3.0 and round it, it'll be 180. Well, yeah, let's just do that. I could have done that in my head. 180 revolutions per minute. And there's our answer for A. So, for part B, it's saying, what is the linear speed of the coin, or what is the velocity, the tangential velocity of the coin when the record spins at this rate? Okay, well, this is, we can say this is the rate right here, 7.85 meters per second squared. That's the acceleration. And 7.85 meters per second squared. And the radius at that point equals 0.15 meters. Can we solve for tangential velocity? We sure can. We know that centripetal acceleration equals velocity squared over the radius. So we can say that the tangential velocity is going to be the square root of the radius times centripetal acceleration. 0.15 meters times 7.85 meters per second squared. So velocity is 1.09 meters per second. There it is. Now again, actually, I just did this all myself in real time right now because I hadn't done it previously because we just added this before I recorded this. So hey, let me know if I'm wrong, if I got something different, or if I made a mistake. I very well may have. Okay, but that's what I get, and that's at least the process we would use. So let me know if you see any discrepancies between my answer and yours, and I'll see you in class.